Next example of subspace. W is equal to xy belongs to r square, such that x raised to 4 is equal to y raised to 4, or x raised to 4 minus y raised to 4 is equal to 0. This example is like x square minus y square is equal to 0. So we have to discuss this W is subspace of R square or is not subspace of R square. So W is XY order pair XY belongs to R square such that x raised to 4 is equal to y raised to 4. This is not subspace as. Why is not subspace? Because we have the counter example for addition, property addition. So take U as 1 minus 1 and V as 1 1. So these are the element of R square. Similar to this example is similar to example that W is equal to XY belongs to R square such that x square minus y square is equal to 0. This is x raised to 4 minus y raised to 4 is equal to 0. This is not close for addition because if we take U as 1 minus 1, this is the element of this W because 1 raised to 4 and minus 1 raised to 4 both are same. And similarly, V as 1 1 is the element of this W because 1 raised to 4 and 1 raised to 4 both are same. So belongs to W here, right? The belongs to W. These are the element of W, right? Here belongs to W here, right? W. But U bar plus V bar. What is U bar plus V bar? Is 1 minus 1 plus 1 1 is 2 0. And this does not belongs to W, right here W. Not it is not R square. It is W here, right here W. So this 2 0 addition of these two element of W, these are the two elements of W, but their addition is not element of W because 2 0 not satisfied this property that 2 square is 4 and 0 square is 0. 4 is not equal to 2. So 2 0 is not element of W, and therefore W is not subspace of R square. So right here W notation, here W notation. Okay. So we have the counter example. W is not close for addition. Addition of every two elements of W is not the element of W. So next example, C example. So the set is what? X, Y, Z belongs to R cube such that X is equal to Y plus Z by 2. Or 2X is equal to Y plus Z. Or we say 2X minus Y minus Z is equal to 0. That is, this is the example of the type Ax plus By plus Cz is equal to 0. And it obviously is subspace. That is, if after simplification, this equation, what we have? 2x minus y minus z is equal to 0. And this is the example of the type Ax plus By plus Cz is equal to 0. A is 2, B is minus 1, and C is minus 1. So this is obviously subspace. So we can show after simplification or directly we take the two elements from W, suppose x1, y1, z1 as u and x2, y2, z2 as v, or u bar and v bar, right? Bar or without bar be the element of W. Obviously, these are the element of W. Therefore, these two elements satisfy this condition. That is, x1 is equal to y1 plus z1 by 2, and x2 is equal to y2 plus z2 by 2. Now we have u bar plus u bar plus v bar, or u plus v is equal to x1 y1 z1 plus x2 y2 z2 is what? X1 plus x2 y1 plus y2 z1 plus usual addition. And now we have to show this is the element. This is the element of W. So when this is the element of W, if x1 plus x2 is equal to y1 plus y2 plus z1 plus z2 by 2, that is, this element satisfies this condition. X is equal to y plus z by 2. This is equal to this plus this divided by 2. So consider x1 plus x2. And what is x1? x1 is y1 plus z1 by 2. x2 is y2 plus z2 by 2. So take the 2 as LCM. So we have y1 plus z1 plus y2 plus z2. And then we have y1 plus y2 plus z1 plus z2 by 2. That is, we have this x1 plus x2 as y1 plus y2 plus z1 plus z2 divided by 2. That is, arrange this sequence of these elements. We have this. And therefore, u bar plus v bar belongs to W. As u bar and v bar, for all u bar and v bar belongs to W, because u bar and v bar are, or u and v are any two element of W and their addition belongs to W. So the first property that W is close for addition is true. Now take K as any element of R, that is a real number, that is a scalar, any scalar. And then Ku is what? K x1 y1 z1 is K x1 K y1 K z1. This is the usual multiplication, scalar multiplication definition in R3. Now consider kx. So now we have to show this is the element of W. When this element is the element of W, if kx1, if this element satisfies this property, that x is equal to y plus z by 2, that is if kx1 is equal to ky1 plus kz1 divided by 2, then we say that this is the element of W. So then consider kx1 is equal to k. What is x1? X1 is y1 plus z1 by 2, that is ky1 plus kz1 divided by 2, and this is the element of this type. This is the element satisfies the condition that kx1 is equal to ky1 plus kz1 by 2, and therefore ku bar or ku belongs to W, and therefore ku belongs to W for all scalar k and for any u belongs to W, and therefore W is closed for scalar multiplication. Therefore W is a subspace of V is equal to R3, because W or elements of W satisfies both the conditions, that is W is closed for addition, W is closed for scalar multiplication, and therefore W is a subspace of R3. Now the fourth example, W is XYZ W belongs to R raised to 4. This is 4 tuple, and the condition is YZ plus W is equal to 0. This is not again the subspace. Why? This is not subspace. As we have the counter example, this is not closed for addition. W is not closed for addition. So take U or U bar as 0, 1, 0, 0. This is the element of W. Why? Because this element satisfies this condition that Y into Z is 1 into 0 is 0 plus W is 0. So y into z 1 into 0 is 0 and plus W 0. So this is the element of W. Also this is the element of W V. What is it? Y, this 0 0 1 0, because 0 into 1 is 0 plus W means 0 is equal to 0. So these two are the elements of W, right? Belongs to W, right? Belongs to W. Don't write it is belongs to R raised to 4. Belongs to W. These are the two elements of W. But what is their addition? U bar plus V bar, or U plus V is 0 1 0 0 plus 0 0 1 0 is equal to 0 plus 0 is 0, then 1 plus 0 is 1, and 0 plus 1 is 1, and 0 plus 0 is 0. That is the addition of the corresponding components or usual addition. And if we observe this element 0 1 1 0, it is not the element of W. It is not satisfying this condition because Y into Z is 1 plus W is 0. So 1 plus 0 is not equal to 0. It is equal to 1. And therefore this does not belongs to W, right here W. And therefore W is not closed for addition. And therefore W is not a subspace of R raised to 4. So observe these 4 examples. So next example, Ax is equal to 0 is the homogeneous system of m linear equations in n unknowns. Then the show that the set of all solutions of the system is subspace of R raised to n. Obviously W is what? X belongs to Rn such that Ax is equal to 0. That is the set of solutions of the system. X is equal to 0. What is W? W is the subset of R raised to n and is the set of all X belongs to Rn such that Ax is equal to 0. That is the solution set. Is the set of all solution of the system Ax is equal to 0. And now we have to show this W is subspace of R raised to n. Obviously 0 belongs to Rn because A0 is 0 and that is W is not equal to 5, and obviously W is subset of R raised to n. So write that directly that W is not equal to 5 and W is subset of R raised to n. Now we have to show W satisfies the two conditions. That is the addition of every two elements of W belongs to W. So first take two elements x1 and x2 belongs to W, and KB and LB any scalar. Okay, this is the conditions, single condition of subspace. Don't use this condition. We use the separate two conditions. That is, suppose x1 and x2 belongs to W. Then what do we have? Ax1 is equal to 0, Ax2 is equal to 0 because x1 and x2 satisfy this condition. And now consider x1 plus x2. A in bracket x1 plus x2 is ax1 plus ax2, and that is equal to 0 plus 0 is equal to 0, and therefore x1 plus x2 belongs to W. And next take k as any scalar and x1 as the element of W, and then Consider a in bracket kx1 is kax1, and that is k into 0, and that is equal to 0, and therefore kx1 belongs to w. And so by using that two condition, we show that this w is a subspace of r raised to n, right? So the separate two condition, this is single condition, kx1 plus lx2. So next is the v is r square, and vector addition and scalar multiplication defined as normal. As normal means usual scalar multiplication and usual addition are defined on this vector space R2. Let W is xy such that x is equal to 0. Show that W is subspace of 0. So this is the x coordinate compulsory 0. So these are the element of W, and now we have to show this is the subspace of V or R2. That is why I have to show the two conditions. So the two conditions are what? We show that the addition of two elements of W belongs to W. So take U bar as x1, y1 and V bar as, or V as x2, y2 be two vectors in W. And then x1 and x2 equal to 0. Now what is u plus v is x1 y1 plus x2 y2 is x1 plus x2 comma y1 plus y2, and here x1 and x2 are 0, so their addition is 0. So this element is 0, and therefore this element x1 plus x2 comma y1 plus y2 belongs to w, because this x1 plus x2, this first place element x coordinate is 0. Similarly, k into u is k x1 y1 is equal to k x1 k y1, and this is the element of w because kx1 is 0. X1 is 0, therefore kx1 is 0 for any scalar, and therefore this is the element of w because its x coordinate is 0. And therefore what we have, w is closed for addition, or addition of every two elements of w belongs to w, and scalar multiplication, w is closed for scalar multiplication, that is any element u of w and any scalar k, its multiplication belongs to w, that is w is closed for scalar multiplication, and therefore w is subspace of v. So v is equal to r2 is a vector space under the usual addition and usual multiplication. Let w is equal to xy such that x is greater than or equal to 0. Show that w is not subspace of v. So I have to give the counter example. That is, we have to show this w is either not closed for addition or either not closed for scalar multiplication. So here this is the w is not closed for scalar multiplication. So let u is equal to 1 1 2, or u bar as 1 2, and this is the element of w because its x coordinate is 1 and is greater than or equal to 0. Then take scalar as k is equal to minus 1, and then what happens, k into u is minus 1 into 1 2 is minus 1 minus 2, and this does not belong to w because its x coordinate is minus 1 and it is not greater than or equal to 0, and therefore w is not subspace of v, or w is not closed for scalar multiplication. Second property fails for w, that is any scalar and any element of w, its multiplication does not belong to w, and therefore w is not closed for scalar multiplication, and therefore w is not subspace of v. Similarly, this example, v is a vector space of all real valued function defined on closed interval 0 1, and w is the set of function f from v such that f of 1 half is 0, and therefore w is subspace of v. So we show the addition of two element of w belongs to w. Take two element f and g belongs to w. Then f of 1 half and g of 1 half are 0 because of this condition. And what is considered f plus g 1 half is what? F of 1 half plus g of 1 half is equal to 0 plus 0 is equal to 0, and therefore f plus g belongs to w because f plus g satisfies this condition. Similarly, k is in scalar, then k f 1 half is what? K f of 1 half, and k into 0 is 0, and therefore k belongs to w because kf satisfies this condition, and therefore w is closed for addition as well as scalar multiplication, and therefore w is subspace of v. Similar example, the w r3 v is r3 and x y z such that x plus y plus z, show that w is subspace of v. Obviously this w is subspace of v by taking two elements, show that their addition belongs to w and scalar multiplication belongs to w, and therefore w is subspace of v. Similarly, this example, x square minus y square is equal to 0. This w is not subspace of v, is not closed for addition, or we say the condition is what? X square is equal to y square. So this is again, these are the two elements, 3 minus 3 3 1 and 4 4 minus 1. These are the element of w because minus 3 square is 9 and plus 3 square is 9, 9 minus 9 is 0. and 4 square is 16, minus 4 square is 16 is 0. So these are the two elements of W, but their addition does not belong to W because their addition is 170, and this is not element of W because 1 square minus 7 square is not equal to 0. It is equal to minus 48. And so the W is not closed for addition in this example 2.34, and therefore W is not subspace of R3. Okay. Next is W1 and W2 are subspace of V. Then show that their intersection W1 intersection W2 is also subspace of V. So we have to show W1 intersection W2 is closed for addition and is closed for scalar multiplication. That is, take two element U and V belongs to W1 intersection W2. Right? Either bar U bar V bar or just write U and V belongs to W1 intersection W2, and K be any scalar for the second condition. Then W1 and W2 are subspaces of V. So U bar plus V bar belongs to W1. U V belongs to W1 intersection W2 means what? U and V belongs to W1 as well as U and V belongs to W2. U and V belongs to W1 and W1 is subspace. So U plus V belongs to W1 and U and V belongs to W2, and W2 is subspace means the addition of U plus V also belongs to W2 as well as U plus V belongs to W2, as W1 and W2 are subspaces and U and V both belongs to W1 as well as W2, and therefore their addition belongs to W1 as well as their addition belongs to W2, and therefore U plus V or U bar plus V bar belongs to W1 intersection W2 because U bar plus V bar belongs to W1 as well as U bar plus V bar belongs to W2, and therefore their addition belongs to W1 intersection W2. And similarly, we can show that this condition, that is, suppose U is the element of W1 intersection W2, so U belongs to W1 as well as U belongs to W2, and K be any scalar, then K U bar belongs to W1 and K U bar belongs to W2 as W1 and W2 are subspaces, and therefore K U bar belongs to W1 intersection W2, and so W1 intersection W2 is subspace of V. So intersection of two subspaces is subspace of the same vector space, but union is not necessarily subspace of the that vector space. That is, if W1 and W2 are subspaces of V, then W1 union W2 is not subspace of V. So this is the problem. So we give the counter example for this. That is, this statement is not true. So let V is equal to R square and W1 as XY. X belongs to R and W2 is 0Y. Y belongs to R. Obviously, these two are subspaces of V is equal to R2. Then W1 and W2 are subspaces of vector space V. And what is W1 union W2 is subspace of V, but W1 union W2 is not subspace. W1 intersection W2 is subspace of V, but W1 union W2 is not. Here write intersection, or crash this sentence. W1, what is W1 union W2? What is W1 union W2? Their union. So if we take 1 0 as the element of W1 and 0 1 as the element of W2, so these 1 0 and 0 1 belongs to W1 union W2. Why? When the element belongs to W1 union W2, either element belongs to W1 or belongs to W2. So 1 0 is the element of W1. That's why 1 0 belongs to W1 union W2, and 0 1 belongs to W2. Therefore 0 1 belongs to W1 union W2. But their addition 1 0 plus 0 1 is 1 1, and this is not element of W1 union W2 because 1 1 does not belong to W1 as well as 1 1 does not belong to W1. So when the element 1 1 belongs to W1 union W2, either 1 1 belongs to W1 or W2, but 1 1 does not belong to W1, does not belong to W2, and therefore 1 1 does not belong to W1 union W2, and therefore W1 union W2 is not closed for addition, and therefore W1 union W2 is not subspace of V. W1 and W2 both are subspaces of V, but their union is not subspace of V. So this counter example shows that if the W1 and W2 are subspaces of V, then their union is not necessarily subspace of that vector space V. So these are the examples for Exercise. Determine the following are subspaces of R3. set of all vectors of the form x111. This is again not subspace, because if we take the two vectors of this type, that is 211 and the 311, their addition is 522, and this is not the element of this set. That is it is the set of all vectors of this type. So it is not closed for addition. Set of all vectors of this type, this is closed for addition and scalar multiplication. This is the second number. B is this set is the subspace. Similarly, this set is subspace. Y is equal to x plus z means it is of the form x minus y plus z is equal to 0. This is the condition. Is of the form ax plus by plus cz is equal to 0, and this is the subspace. So x plus y is equal to 7. This is not subspace. Okay. Then y is equal to 3x and z is equal to 5x. I think this is not subspace. This is not subspace. So these are the subset of m2 by 2r w. These are the m2 by 2r is what? Subspace of all. This is the vector space of all 2 by 2 matrices with real entries, and these are the some subsets of m2 by 2r. This again, this is the B and D are 0. B and D are 0. So some of them are subspaces, some of them are not subspaces. Determine which of the following are subspaces of P3. What is P3? P3 is the set of all, is the vector space of all polynomials of degree less than or equal to 3 with the real coefficients. Okay, P3. So the W is what? Px a0 plus a1x plus a2x square plus a3x square belongs to P3 such that a0 is 0. Compulsory a0 is 0. So this is the close for addition and scalar multiplication. So W is subspaces. So some of them are not subspaces. I think this is again the subspace or not subspace. A0 is an integer. This is not subspace, because if you take the scalar as 1/2 and you take the element of W, then this a0 becomes non-scalar, a non-integer, and therefore it is not subspace. So these are the examples of on P3. This is the example on function space. So union is then show that W1 and W2 are subspaces of vector space P. Then show that W1 union W2 is subspace of V, but when, if and only W1 is either subset of W2 or W2 is subspace of W1. Now, usually this W1 union W2 is not subspace of V, but when it is subspace of V, if and only this. So remember this condition. The solutions are given. So solution of these problems. So X and Y, already these problems are discussed. X and Y, this is the subspace. We have to show the close for addition and scalar multiplication. So these are the examples for homework. So solve all these examples, exercise examples, and share its answer with me. So this is about the topic subspace. So we have to determine the set is subspace or is not subspace. That is, subset of vector space is subspace or not subspace. So just when the subset of vector space is subspace, if the subset is closed for addition and scalar multiplication, that is, the addition of two elements of W belongs to W, and the addition, the scalar multiplication of any scalar and any element of W belongs to W, then we say that the W is subspace of V. And when W is not subspace of V, out of these two conditions, any one fails, then we said it is not subspace. So we will discuss the next topic, linear combination and linear span, in the next lecture.